شنجو كيف حالكم؟ المرة اللي فات حكينا على الكلمات، كيف تخلي الكمبيوتر يفهم الكلمات. تمام، بس اللغة مش كلمات بس. فاليوم حنحكي على language models. جهزوا عقولكم، خلونا نبدو. So today we're going to go beyond the word level. We're going to talk about more than just words. Last time, as I was saying, we talked about word embeddings. So we talked about being able to compare two words for their actual meaning using a quantitative representation. But today we're going beyond that. We're looking at words in context. And the reason that okay. So like I was just saying, we're going to be talking about more than words today. We're going beyond the word level. Last time we looked at word embeddings, understanding words using vectors and things like that. This time we're going to have a computational model for whole texts or whole sequences of language. It could be phrases, sentences, paragraphs, documents. We're going beyond the word level today. And as we're talking about this today, as last time, I'm skipping over decades of amazing research in natural language processing, and I'm going right to the state of the art and the current models that are being used today. Another thing to point out is that what I'm going to tell you today about language modeling and about going beyond the word level is that a lot of the newest techniques are performing the best on English, and other languages need more work in order to have models that will work for them. So I hope that's something that helps us move forward in multilingual natural language processing as well. Anyways, so today we're going into more than words. So let's start with this. Okay, in Arabic, let's try to fill in those words, right? So somebody tells you happy birthday or something like that, and then you say, Kul winta what? Okay, you probably know Kul winta bkhair. You know better than I do. Now try to fill in these blanks. This may be a little bit harder. اللي يستخدم السيف. How do you fill that in? Okay, probably بسيف يموت, or يموت بسيف, right? Okay, and even harder maybe, like say you just have thank you blank blank blank. Okay, how would you fill that in? It's a little bit less clear. You could come up with 3 words to come after thank you, but it's a little bit less clear exactly what you mean. But any of these things are, basically places where you would use text autocomplete, right? The first one, it's pretty obvious what the next word. The second one is also fairly obvious, but it's not as common of a phrase as the first one. And the third one is like, it's an open question. Like, there's lots of ways to fill that in, but there are common ways to fill it in. Autocomplete has to deal with all of these different kinds of settings. But what about this kind of filling in the blank? The computer says, كيف نقدر نصدق, and then you respond, أنت, like when was the أنت بنيت المدينة قديمة, okay? And what does the computer respond to? How does it respond? It needs to respond with a lot of things, with knowledge about Medina Qadima and when it was built and all that kind of stuff. But it also has to phrase that knowledge appropriately. So generating human-like dialogue, it's like it's, I don't know, another level of needing to fill in the blank, needing to model the actual language that is being talked about there, right? So this gives you kind of a sense of what kinds of things are necessary in doing language modeling when we're going beyond just comparing words with each other. So Again, this task is called language modeling or building language models, LMs. And we're going beyond the word level. Last time we took one vector and another vector and we did like a cosine similarity between them, and you can get a number representing how similar are these two words. But that's not going to serve us if we're trying to do some of these tasks like filling in the blanks and stuff like that. So we need to model what words look like in context. Okay. Now, one of the simplifying assumptions that is usually taken in language modeling is that we're going to approximate language as a word or character sequence. It's just a sequence of words one after the other, and um, and if we model language that way, it's not the only way to model language. Then we can start calculating things over that sequence of words or characters. And we've actually found this to be pretty good in practice, despite there being tons of other research about ways to represent languages and calculate models over them. The older models were n-gram probabilities, and it's not necessarily older, it's still a very viable um, paradigm here, but n-gram probabilities, and what that is, gram is like word or token, and so we're looking at n grams at a time. Like so, for here are trigrams or 3 grams at a time. So this is saying thank you for, and it's comparing. This is a probability here, p of 4 given thank you. In other words, given the words thank you, what's the probability that the third word or the next word is 4? And so that's a trigram probability. And what you're doing is you're comparing that against the probability of thank you for versus thank you that, or other possible completions after thank you. So those were n-gram probabilities, and you could look in large corpora and directly calculate n-gram probabilities. Or you could use some other means to calculate them with intermediaries and stuff like that. More recently, deep learning models have been making language models using recurrent neural networks, and I'll show you an example of one later. Well, not so much in detail, but I'll show you what it looks like. And then people most recently have been using attention within deep learning frameworks in order to do language modeling. So before I show you what it looks like, again, this is still high level what it looks like. Let's look at some of the state-of-the-art language models in action. Okay, so the top one for human-like text generation is the OpenAI GPT-2 model, and it produces human-sounding text of many different genres, and the use it for everything kind of tool is BERT, bidirectional encoder representations from transformers. And it's kind of a riff off of, there was a previous model called Elmo in the word embeddings space. And so that was a Sesame Street theme. Here, BERT is also a Sesame Street theme. So there is some humor in the computational community. Anyways, BERT gives you human-like prediction, and pretty much any task that you would want to do, it does it. All right, so here's the OpenAI GPT-2 model. It's it's at this talktotransformer.com is using this model, and you can basically type in whatever prompt you want, and then it'll complete the text. So I typed in here, to whom it may concern, I'm writing to apply for the data science position as originally posted on LinkedIn, and it's given me a completion of that text. I'm writing this, and so you can see what it's done here. I'm a senior engineer at Sysdig.com, and have been for 3 years now. I have a PhD in computer science, MS. That's a little interesting, and 3+ years of experience designing and implementing performance tests and simulations for various processes and applications in my personal and professional life. That's a mouthful, but this is the kind of thing that you would find in a job application cover letter, right? That's kind of what I was writing here, a job application cover letter, how you start something to say, I want this job. And then it starts talking about the qualifications. And look at this, it even says sysdig.com, this is where I work, and it refers back to that same company name. So this is pretty amazing kind of generation. This text generation works with basically any type of genre, and it should be able to pick up the genre. Um, and so we could say the Duke men's basketball team. This was my alma mater, the Ware College, improved to a 17-2 mark on the season as they downed the Syracuse Orange last Thursday at 9 p.m. at Cameron Indoor. So maybe you don't know about college basketball, but this is like a sports article saying this is what happened. And here you start seeing some of the lingo that is common in talking about basketball games. Here, Notre Dame is also in the same conference for basketball only. So lots of able to generate really neat things here. The BERT language model is a little bit harder to visualize exactly how it's so useful. BERT is able to be used in so many different downstream tasks, but to figure out, but to visualize how it's used by itself, this is one of the ways you do it is by the exact fill in the blank kind of thing that we were talking about earlier. So here I have it set up, thank you for meeting blank, blank, blank. And it says, thank you for meeting me here today. Thank you for meeting with me today. Thank you for meeting me, sir. Thank you for meeting us here today. You know, these are all probable, very likely possible completions of these of that phrase. But with language models, with BERT language models, you are able to also do something different here. You can put in, you can do, you can fill in different blanks. So thank you. How would it fill in these different words? And it's thank you for meeting me today. Thank you for meeting me here. And then thank you about meeting with me. Thank you before meeting with me. It's a little bit weird, but you can see that the probability for those are much lower. All right, so we have an idea of what these state-of-the-arts models look like in action. So what do they look like in terms of their architecture and the technical side of things? Again, not going to go into really fine detail, but the earlier models, the RNN models, recursive neural network models, here's one of them, the LSTM, standing for long short-term memory. And the basic idea here is that we're trying to predict the next word, and in order to predict the next word, you're going to send the current word through a bunch of linear algebra and deep learning, nonlinear layers of deep learning kind of blocks. So and so you go through all this stuff, all this computation, and get out, the idea is that you get out these words. The representation for these is usually embeddings, word embeddings that you had from last time. You can also train them from scratch, but usually you start with word embeddings and you produce word embeddings on the other side as well. And then you do softmax to find the other side. But the basic idea is with a RNN or long short-term memory, the LSTMs, anything like that, is that you have a recurrent cell here where you're passing information along from left to right, and it's keeping track of certain things and throwing away other things and whatever else. Okay, so there's a passing on from place to place. Now, the OpenAI GPT-2 model that I showed you is different. It uses a different cell. It uses what's called it uses attention. and specifically it uses the transformer. This is a specific kind of attention architecture, and basically it takes inputs, whatever is connected by lines here, it takes those inputs and figures out which ones of them are most important, and then it's going to pass them to the next layer, which figures out which ones are most important from there, and then it produces an output. Okay. Again, here we're looking at the next word or that kind of thing, if we're doing language modeling as our main task. And so the transformer architecture is a different one. It doesn't actually do things passing left to right necessarily, but as you can see with the OpenAI GPT-2 architecture, each place is drawing from the things to its left. So each, like this word here, is attending to the important things in its context from the left, okay, to make its decisions. And the most recent, or the most, I guess, the highest performing state-of-the-art method nowadays for a lot of downstream tasks is BERT. And here, they made a different assumption here. Instead of only having attention, but instead of only attending to things in the past, it also allows you to attend to things in the future. So it's not how human language works. We can't necessarily figure out what is being said based on future words. Or maybe you can. I don't know. That's a sort of philosophy of language kind of question. But in any case, it attends to multiple things before and after it. In order to make this a problem that actually works, we have to mask an input and then predict that word. So we're masking the word I here and then predicting it. You're going to randomly mask some number of inputs and then predict those and the output to do the language modeling here, which is actually similar to some of the word-to-vec models that we talked about before in the word embedding space, masking some context words and that kind of thing. Another note about the training of BERT, you actually do use, in order to do sentence level tasks, you actually also identify that this whole thing is part of sentence A, and then you also predict sentence B at the same time. I just didn't show that here on this model. So that's what I'm going to show you for the technical side of things today. I'm not going to go into the math or whatnot. I'll point you to the original papers for BERT and for OpenAI GPT-2. It should be, if you look for BERT language models, it should be easy to find. Also, I should point out that the LSTMs and recurrent neural networks, when you're talking about language modeling, the best models are bidirectional LSTMs. So similar to how BERT removed the left to right assumption, bidirectional LSTMs where you go left to right, and then you also have stuff going in reverse, right to left. Bidirectional LSTMs and are sort of the state of the art for RNNs, and oftentimes you use another layer of decision logic, not logic, but decision classification, that kind of stuff, using conditional random fields over here. So anyways, if all of that last part, technical stuff, was difficult to understand, I encourage you to read into one of those models, pick one of them and read into it. Look at some articles or blog posts about it. So some of the trends that we find in these language models, because of, especially with BERT, is that we're moving from recurrent neural networks to attention in language modelings, which this means that there are more parameters to learn. Attention takes more parameters, which requires more compute power and more data, but that's available for languages like English. and a few other languages. It's not quite as available, digital data anyways, in some other languages. And another area that we're moving to is, instead of having supervised training where people had to go through texts and say, here's the right way to look at this particular text, you can't do that for all of the web. So we're looking at unsupervised pre-training of language models. In other words, without human labeling things, we're just looking at all of the web data or whatever else enormous amount of text that you have, and we're using that to build the first model of language in BERT or in other pre-trained types of models. And then after that pre-training, unsupervised pre-training, we're doing task-specific fine-tuning. So previously, people had done a whole deep learning neural network for a specific task, like named entity recognition, where you're finding particular entities of interest in a text. So that used to be, you do that ad hoc, you just do that named entity recognition for that specific task. You build a whole neural network. Now, instead of that, we're starting with the language model from BERT and then fine-tuning on top of BERT and to do a task like parsing or named entity recognition, or even things like part-of-speech tagging or chunking or things like that. So lots of the things that we want to do are possible using a base of BERT. It's sort of like we were starting with a base of word embeddings and then building things on top of that. Now a lot of people are starting with the base of a language model and then building on top of that. So, conclusion, we've been talking about words and phrases in contexts, not just isolated words and things like that, trying to get models of whole phrases of language and sentences and beyond that. We've seen some powerful state-of-the-art models. I didn't even talk about the kinds of performance that these models get on other tasks downstream, but they're very useful in lots of other natural language processing texts. OpenAI GPT-2, BERT, very good models. And some of the resources you can look at, you can check out the BERT models. I have the link here. If you want to look at an efficient NLP package in Python, last time or the previous time I mentioned NLTK, which is great for education. Spacey is another good option. These are all Python packages, so if you're going to do NLP, I highly encourage you to check out Python and get your Python chops up if you don't already have them. There is also a decent amount of stuff in Java, but Python, I think, is the easiest, has the most resources for this stuff. And finally, like our facebook.com Libya AI page, and check out our next video when it comes out. Thank you. God bless.